Well, good morning, and welcome to the penultimate lecture in April. We are marching right along here. So, whoa! All right, see this here. So this is evidence that I have been playing around with digital adult coloring books. That is why my pen settings are all out of whack. Let's change those up. We're going to change from dry metal brushes back to something a little more default. So you want it, not that big. Yeah, around 25. And we don't want the opacity. I messed up the thumbnail. Oh, goodness. Raj, you are always first, or usually first enough that I think always. We got another daily mixtape. Up in this situation. Oh, let me check. Okay, good. It's actually a little thicker than I normally like it. There we go. Our daily mixtape today goes by the title of Don't Die. And you can find it. You can find it on the link to the playlist in the description. Is that what that's called? I'm learning. You guys are helping expand my vocabulary. Apparently, a gunner is someone who always gets the first comment in, which would make Vraj definitely the gunner for this class. Of course, you could always look to dethrone him by getting in here earlier and pinging that first comment. I try to log in or start the stream about 5 minutes ahead of class just to, kick it, say, hey, as everybody kind of wakes up and rolls out of bed, gets to lecture. So yeah, you can check out the daily mixtape. I'm still on a hip hop kick. No idea how long it'll last. But it's what I'm rolling with. Business. Let's talk some business. I believe. Oh, hang on. Oh my. I need a bigger eraser. Maybe not that big. I gotta double check something. There we go. All right, so we got a couple business items. For those of you who have not been looking at the syllabus, ACS homework 7 and 8 are due today. So this is, I guess, just a friendly reminder to keep looking at the syllabus. Oh, okay. I'm learning things about gunners. Try hard in the class, read first, know it all, but usually first most active in the class. Hey, are there any chance we're still going to get those? Heck yeah. Ryan, great question. Absolutely, Ryan, and thanks for the reminder. Actually, I will be going, because I had it's been on kind of my list of things to do, but not near the top. I will make sure that those get added today. So I'm planning on adding them to the exam to take home. The exam to take home score. So that's where you will see the bump in the 12 points. I will get that done today. Thank you for the reminder. What else? We got the ACS. Oh, right. Okay. I wanted to say a quick something about lab exercise 5. So lab exercise 5 has 3 things. Well, more than 3 things, but there's 3 main things in lab exercise 5. There's Lewis structures. We got Lewis structures. We have VSEPR geometries. And we have hybridization. All right. And of these 3 things, so they give you a bunch of molecules and they want you to do all of them. You can do the Lewis structures for all of them right now. And the good news is the VSEPR geometries and hybridization, you can totally add this later. So I would recommend starting on exercise 5 because it's fairly long. Draw out all the Lewis structures, double check them, make sure you're good to go there. Then after this week, between today's lecture and Wednesday's lecture, we'll be covering VSEPR geometries and enough hybridization for you to be able to label everything. And you'll be able to go back and add those. But I would start doing the Lewis structures now. By the end of today's lecture, you'll be able to do some of the VSEPR stuff. By the end of Wednesday's lecture, you'll be able to do all VSEPR, and you'll know enough hybridization to be able to label it. Cool? Alrighty. So, with that being said, let's go ahead and dive into today's lecture. All right. So, up to this moment in time, our focus as far as depicting molecules, drawing covalent molecules, our focus has been Lewis theory. All right, Lewis structures. And Lewis structures are great. They're very good, reliable for depicting the structures of covalent compounds that are made up of main group elements, and anyway, it's been our first real introduction to start thinking about molecular structures. But as we're going to see, there's a major drawback to Lewis structures. Okay, here, hang on, I'm getting a question. Let's see, exercise 5. There's a problem that goes over not technical. That wasn't sure. Went over. Oh, okay. Actually, if you look, Raj, great question. I actually did the Lewis structure at the end of last lecture. Oh, there we go. NO is something called a free radical. It has an unpaired electron, and yes, it does have less. There's no way to satisfy the octet rule for nitrogen. You can see the end of last lecture to hear me talk about that a little more. All right. Now, Lewis structures are great because they show connectivity. All right. They show how atoms are connected and what atoms are connected. And the bond order, they show us whether we're dealing with a single, double, or triple bond. All right, so Lewis structures show us connectivity. They do not, however, depict the shape of a molecule. All right, and that is where we're going to start talking about VSEPR. All right, VSEPR theory takes the information of a Lewis structure. It uses a Lewis structure to predict the three-dimensional shape of a molecule. So you need one to do the other, and as we learn VSEPR, we will be looking at the Lewis structures and then using those to predict the three-dimensional shape of a molecule. All right, and so now at this moment in time, we're going to be taking our knowledge. So we're going to be looking at Lewis structures and learning how VSEPR takes those structures that we already know how to draw and uses the Lewis structure to predict what three-dimensional shape a molecule will have. So here's how it does that. So VSEPR stands for valence, shell, electron, pair, repulsion theory. All right, that is what VSEPR stands for, and this is where the VSEPR comes from. Valence, shell, electron pair, repulsion theory. Oh yeah. It's so valence, shell, electron pair, repulsion theory. It could also be valence, electron, shell pair. I think the correct is VSEPR, not VESPR. No, exercise 5 says VES. I'm confident that EPR is the right way to go. But it doesn't really matter. It doesn't matter all that much. Okay, and what valence, shell, electron pair repulsion theory has a very simple premise. The premise is this: electrons repel each other. They repel each other and try to get as far away as possible. As they can. All right. So take, for example, the molecule of methane, CH4. Oops. So here's the Lewis structure for methane, for CH4. Everybody's got a full octet. Everything's happy. One of the things you'll notice, if you measure the angle, something called the bond angle. So if we take 3 atoms in sequence and we measure the angle that those 3 atoms make, this is called a bond angle. This right here, this angle is called a bond angle. And this, as drawn, has a bond angle of 90 degrees. All right? Now, here's the thing. Every bond, remember, every bond is made up of electrons, and electrons repel each other. They want to get as far away from each other as possible. The farthest, and you can see that in this molecule, we have 1, 2, 3, 4 bonds. The farthest 4 bonds or groups of electrons can get from each other in 2-dimensional space is 90 degrees. But methane, the molecule, does not live in a 2-dimensional universe. It lives in our 3-dimensional universe. So in 3 dimensions, it can take these bonds, can get farther away from each other and take on wider angles. And I'm going to show you what that looks like here. All right. So here I've got my carbon. All right. And let's see, I'm going to draw. Actually, no. These are going to be in green. All right. Then we've got 2 more H's. All right. Now, to understand the picture that I've drawn, I've color-coded this. Yeah, it's going to be wider than 90. It's going to be, and we'll see. So I've color-coded this. If you haven't ever seen this type of drawing before, let me give you a key. So in green, you can see that I've drawn some lines here. Lines are we call in plane. They're in the plane of the screen, so they're flat with the screen. Hang on 1 second. I'm typing an answer to a question. Sometimes I can multitask. Sometimes not as well. Okay, so the green bonds, the green hydrogens, are in the plane of the board or the page or the screen, I guess, at this stage in time. The one that's kind of in that orangey salmonish color, that wedge is coming out of the screen towards you. So it's reaching out towards you. And then in yellow, you can see that kind of dashed wedge. That is back behind the screen, pointing away from you. All right, so it is going away. Did I write the wrong one in plane? Plane PLAIN. All right, so this is a 3-dimensional drawing of the molecule of methane, and if you measure the bond angle here comes out to be 109 degrees. All right. And this is as far as 4 different groups of electrons all around the same atom can get from each other in 3-dimensional space. All right. Now, so we are about to kind of go through and use geometry and the fact that we know these electrons want to get away from each other to analyze what shapes these molecules will take based on their Lewis structures. And so, oh man, I feel like there's something I wanted to say. I'm sure it'll come to me in a second. All right, so I want to lay down a few things here. So we're gonna have, let's see, the Lewis structure. We're going to have here are our categories: electron groups, lone pairs. Then we're going to have something called the electronic geometry. And then something else called the molecular geometry. Finally, let's see, I'm going to just make a little more space here. All right, finally we have the 3-dimensional representation plus our bond angle will be our last categories. All right. Just to give everyone a kind of a legend for what these oh wait, no, I didn't want to delete that. For what these different categories are. just so we're all on the same page. LS. This is a Lewis structure. The electron groups in your exercise 5, exercise 5 calls these electron domains. All right. So you'll see, those of you who have looked at exercise 5 already know they ask you how many electron domains. These are what I'm calling the electron groups. The electron groups is equal to the sum of the number of bonds plus, sorry, not the number of bonds. It equals the sum of attached atoms plus the number of lone pairs around an atom. That will give you your electron domains. It's the attached atoms plus the lone pairs. Just to make sure we're all on the same page, when I say LP, I'm talking about a lone pair of electrons. All right, so Lewis structures, electron groups, lone pairs. Now, electronic geometry and molecular geometry. When I talk about the electronic geometry, is the shape made by the electron groups. All right, the shape that all the electron groups make around the central atom. When I talk about the molecular geometry, I'm talking about something different. All right, the molecular geometry is the shape made by the atoms alone. All right, so the difference between these two is electronic geometry includes lone pairs, molecular geometry excludes lone pairs. All right. Okay. So that is what all of these categories mean. And we are going to the goal of this whole exercise. So let's remember why we're doing this. We are going to take the Lewis structure of a molecule. Oops. We are here to take the Lewis structure of a molecule and use it to find, to draw the three-dimensional representation and the bond angle for said molecule. And the way you do it is by first analyzing your electron groups, because your electron groups will tell you what your electronic geometry is, and then you look at your lone pairs, and the number of lone pairs will determine what the molecular geometry is. And once you have all of these things pinned down, you can draw a three-dimensional representation of the molecule. All right? So with that kind of out of the way, let's go ahead and and begin using this analysis. And we're going to start with carbon dioxide. All right. Now, if we look at the Lewis structure for carbon dioxide, looks like so. Which you could take time to calculate the electrons, draw it out. The reason why I'm doing this faster here is because the point of this lecture isn't Lewis structure practice. That's what exercise 5 is for. We're here to analyze a Lewis structure for its VSEPR geometry. Now, when we talk about the number of electron groups, we are only looking at the central atom. All right? The central atom in carbon dioxide has 2 atoms attached, and 0 lone pairs. All right, so we can put that down. We know that we have 2 electron groups. None of them are lone pairs. And whenever you have 2 electron groups, your electronic geometry is called linear. All right, 2 electron groups means that your electronic geometry is linear. Whenever you have 0 lone pairs, your electronic geometry and molecular geometry are the same. Remember, electronic geometry is the shape of all electron groups. Molecular geometry is just the shape of the atom. Since we don't have lone pairs, they're going to be identical. So with 0 lone pairs, your electronic and molecular geometry are the same. All right. Now, a linear geometry. Oops. Dang it. I knew I was going to mess that up. A linear geometry will have the 2 electron groups, all right? So the 2 atoms attached to the central atom will be as far away from each other as possible, which in a linear geometry is 180 degrees. So it turns out that the 3-dimensional representation of carbon dioxide looks just like its Lewis structure. We have a bond angle of 180 degrees, and we have a linear geometry. Cool. Okay. Let's look at our next example. Let's look at formaldehyde. All right. That's not the Lewis structure. That's the chemical formula. The Lewis structure for formaldehyde looks like this. So we have everything attached to our central carbon atom. 2 H's, 1 O. We've got a oxygen-carbon double bond. Now, the first question you ask yourself is, how many electron groups does my central atom have? And this is the key thing to remember. I'm not asking about how many atoms are in the entire molecule. I'm not asking about how many lone pairs are in the entire molecule. I'm just asking for the number of atoms and lone pairs directly on the central atom. And here we have 3 atoms, 0 lone pairs. All right. So we have 3 atoms, no lone pair electrons. All right. Now, whenever you have 3 electron groups, your electronic geometry is something called trigonal planar. All right, trigonal planar. And whenever you have 0 lone pairs, your molecular geometry and electronic geometry are the same. All right. Now, the farthest, so we have 3 electron groups around our central atom. The farthest that 3 groups can get, if they're all attached at the center, in 3-dimensional space is 120 degrees apart. All right. 120 degrees apart. So the 3-dimensional shape for this molecule will look like this. And then in each position we have, well, we have got 2 hydrogens and then an oxygen with a double bond. All right, so this is the 3-dimensional shape for the molecule formaldehyde with its bond angles of 120 degrees. Cool? Okay. Remember how a little bit earlier I was like, oh, I have something to say. I can't remember what it was. Now I do remember what it is. So with respect to so for your VSEPR geometries and bond angles, let's see, geometries, bond angles, and 3-dimensional representations. For all of these are all things that you got to memorize. Or meorize. All right, these are all things you have to memorize. And you you may be thinking, well, do we really have to memorize them? Because with a take-home exam, I can just look these up. You totally can. But what I can say is if you don't have them memorized, you're going to lose valuable time on the multiple choice exam. And so you want to have these memorized so you can spit them out as fast as you can for that timed context. So I wholeheartedly endorse having these so at the tip of your tongue, on the top of your head, that you can just spit them out without thinking twice. Okay, Raj, question. Yep, that is 100% correct. The reason, so Raj's question is, is the reason why our bond angles are 120 degrees, is the reason because 360 degrees is a circle, and if you divide that by 3, then it comes out to 120 apiece. That is absolutely correct. Oh, I'm trying to send this comment. It's not sending. It's because I typed "that is correct" in my emoji search. Awesome. Okay. All right. So heartily recommend. I meant to say this at the beginning, so sorry for the interlude in between. Heartily recommend memorizing these VSEPR geometries. All right. Now, Let's do another example. Let's analyze the Lewis structure of nitrite, NO2 with a -1 charge. All right. When you draw the Lewis structure for nitrite, it's double bonded to one of its two oxygens, single bonded to the other, which will have 3 lone pairs and bear the negative charge, and then the central nitrogen has 1 lone pair. All right. Now, the beginning of VSEPR analysis is we need to look at our central atom to determine our electron groups. And you can see that we have 2 atoms, and 1 lone pair. All right. So we have 3 electron groups. Now, you don't have to do any other analysis to determine the electronic geometry. It's based purely on electron groups. So if we have 3, that makes the electronic geometry trigonal planar. All right, trigonal planar. And we can even start drawing a 3-dimensional representation based only on the electronic geometry. Because there we go. Because we know a trigonal planar electronic geometry is going to have 3 groups around our central atom, and they're going to be spaced about 120 degrees apart, right? These 3 groups are going to get as far away from each other as possible. All right. Now, this is our first instance with a lone pair, so you may be wondering, what's the deal with the lone pairs? How do those affect things? And as I've said before, if you have no lone pairs, your electronic geometry and molecular geometry are the same. All right. But when you have a lone pair, any number of lone pairs on your central atom, your molecular geometry will be different than your electronic geometry, and here's how. All right. Let's go ahead and draw out our molecule. So we've got 2 oxygens, but then that third position is occupied by a lone pair. All right. And with a molecular geometry, the molecular geometry does not consider the shape made by lone pair electrons. It only considers the shape made by atoms. And so when you look, if we just take the geometry that we just put in place and draw the lone pair of nitrogen instead of extended out, as just 2 dots on nitrogen, you can see that the molecular geometry shape is different. All right, it's different than a normal trigonal planar. It kind of looks like a bent line, and that is why the molecular geometry, when you have 3 electron groups and 1 lone pair, is bent. All right, that is the actual name, because it kind of looks like a straight line that you kinked, bent in half. Okay, let's see here. Yes. Oops, hang on. Yeah, 1 lone pair equals 1 electron group. So the reason why we have 3 electron groups is because 2 of our electron groups are atoms, and then 1 is a lone pair. That all together, so these all together give us our 3 electron groups. But there are 3 bonds in 1 lone pair. So here's the thing. You never count the number of bonds. Oops. Only the number of atoms. And the reason why is because here you can see in this structure, we do have 3 bonds, but 2 of them are two. We have one single bond and one double bond, and the electrons in that double bond, even though there's more than the electrons in a single bond, the electrons in the double bond are all occupying the same space. It's that space in between nitrogen and oxygen. So even though there's multiple bonds, the 4 electrons in a double bond are still one group of electron, one chunk of electrons. Does that make sense? Here. Hopefully that makes sense. The double bond, yeah, there's two bonds, but they're all smashed in the same space. They're all one group of electrons. And that's why you only count the atoms. You don't count the bonds, because it doesn't matter if one atom is triple bonded to another. If it's triple bonded, all 6 of those electrons are still one group. And we're just looking at groups. All right, so we've seen that the lone pairs on your central atom will change your molecular geometry, all right? But it also changes your bond angle. All right? When you have a lone pair on your central atom, this lone pair spends all its time on nitrogen, and it pushes on the 2 bonds. It repels them. Here, Ryan and Vraj, I see your questions. I'll get there in just one second. First, I want to explain this. So, the electrons in the lone pair the lone pair repels the other bonded electrons. This is the clutch part. More than a bonded pair of electrons. And as a result, oh, that's ugly. Oh, that's even uglier. Hang on. So they repel the other bonded electrons more than a bonded pair, which results in they constrict the bond angle. All right. With a bonded pair of electrons, they spend some of their time around one nucleus and some around the other. Here, these electrons are on nitrogen all the time, so they actually constrict the bond angle. So it pinches down from, instead of 120 degrees, it pinches it, the bond angle here, by 2 degrees. So the bond angle for a trigonal planar bent geometry is 118. All right. Okay. Sorry, Ryan Brush. Let me see what your questions. Will the possibility of best resonant structures affect the possible VSEPR geometry? Ryan, that is a great question. In this class, you do not need to worry about the effect that resonance will have on geometries. In OChem, you will totally get into that. And it's awesome. Okay, Raj, is that the same type of structure as water? Ah. Raj, interesting observation. We'll see if it is when we get there. I'm being all coy. Okay, Diana. Does electronegativity and polar-nonpolar bonds determine the geometry as well? Okay, Diana, first question. Electronegativity and polarity do not determine geometry. But as we'll see in a few lectures, electronegativity and geometry will determine molecular polarity. Diana, second question. The bent geometry does not always have a bond angle of 118. It does not always have a bond angle of 118, and you'll see why in a few examples. Alrighty, let's see. Okay, so let's everyone, great burst of questions. Let's move to our next example. All right, so let's look at, even though we started with this, let's go ahead and give methane the royal treatment. All right. So, Lewis structure for CH4, we've already looked at it. Wait, did I skip you, Vraj? Oh my gosh, I'm so sorry. Let's see. Why doesn't the electron... the electrons in each pair... Ah, they do. They do. But they're trapped in an orbital together. With nowhere to go. The pull of the nucleus holds them there. That's the thing to remember about electrons, is they hate each other. They don't want to be around each other, but they would rather be around another electron if it means getting close to a nucleus than without a nucleus at all. So it's a compromise they make with themselves. They'll be around other electrons if it means they can be around a nucleus as well. It's kind of like when you go to your friend's birthday party, even though you don't like your friend's other friends, but you still go because your friend's there. Your friend is that nucleus that pulls all of these frenemies into the same space. And what VSEPR geometries are really is just analyzing a party to see how do these frenemies who all want to be at this birthday party for the nucleus, it's looking at the lengths they go to try to get away from each other, even though they're not able to get completely away. They're not leaving the party, but they're still going to hang out in different corners of the room. All right, so we have CH4. Oh, goodness. Eraser malfunctions. Okay, CH4. When we look at the number of electron groups, we got 4 atoms. All right. Now, whenever you have 4 electron groups around your central atom, your electronic geometry will always be tetrahedral. All right, tetrahedral. Now, if you want to see a tetrahedron, those of you who play D&D are at an advantage over everyone else. Look at a 4-sided dice. A tetrahedron, the shape of it is like it's a pyramid with a triangular base, or like I said, if you play D&D, it's the 4-sided dice you use to that you roll for healing potions, or if you're dealing damage with a dagger. That is the tetrahedral geometry. Now, every tetrahedron is drawn the same. All right, you will always have 2 electron groups in the plane of the page or board or screen. 1 bond coming out at you, 1 electron group coming out at you, and 1 electron group going behind the board away from you. We know that when you have 0 lone pairs, your molecular geometry is the same as your electronic geometry. And so now we just have to attach our 4 hydrogens. This is the 3-dimensional representation of a molecule of methane. This is what we burn on the stove to cook. I made breakfast burritos. My almost 2-year-old, it's his favorite food for breakfast, and we'll come downstairs and he'll start pointing at the stove and going, Rito, 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 please. And so this is our 3-dimensional representation. Our bond angle here is 109 degrees. All right. And it doesn't matter which two hydrogens you draw the bond angle in between. It's symmetric. It's the same no matter what. All right, so this is the molecular geometry, three-dimensional representation, and bond angle for a tetrahedron. Now let's take a look at what happens to a tetrahedron when we start introducing lone pairs. All right, so let's take a look at ammonia, NH3. So here, ammonia's Lewis structure looks like so. All right. Now, you'll notice that we have, around our central atom, we have 3 atoms attached. And we have 1 lone pair. All right, 3 atoms, 1 lone pair. So we have 4 electron groups. Before anything else, once you have 4 electron groups, you know what your electronic geometry will be. It'll be tetrahedral. All right, it'll be tetrahedral. And once you know it's tetrahedral, you can draw the three-dimensional, you can start drawing at least the three-dimensional representation, because every tetrahedron is the same. You have 2 bonds, or 2 electron groups, in the plane of the screen, 1 wedged coming out at you, 1 dashed going back behind you. Now, you can place your lone pairs and hydrogens anywhere on this representation, and it will be correct. All right. I'm going to choose to put my lone pairs up here, and I'm going to put my 3 H's down on the bottom. Now, here in this three-dimensional representation, we have 1 lone pair, and as we saw with trigonal planar electronic geometries, when you add a lone pair, it changes the molecular geometry. All right, it changes it because the molecular geometry does not look at the shape made by all electron groups. It only looks at the shape made by the atoms. So the molecular geometry will look like this, which, depending upon how well you can visualize kind of 2-dimensional depictions of 3-dimensional shapes, this thing has a 3-dimensional shape of a pyramid with a triangular base. So this is called trigonal. And this is the critical part. Pyramidal. It is not trigonal planar because it has 4 total electron groups. It is trigonal pyramidal. All right. Now the bond angle here is constricted by our lone pair. Again, just like we saw 2 examples ago, when you have a lone pair, trigonal pyramidal, we'll see a square pyramid a little later. So this lone pair constricts our bond angle, pinches it by 2 degrees. So instead of having bond angles of 109, a trigonal pyramidal molecule will have bond angles of 107. All right, so that is the trigonal pyramidal geometry. All right. Now, that's what happens when you add 1 lone pair to a tetrahedron. How about we try adding 2 and look at the three-dimensional shape of water. All right, now here's the Lewis structure for water. When we look at the electron groups around our central atom, we have 2 atoms. And in addition, we have 2 lone pairs, giving us a total of 4 electron groups. All right. Now, once we see that we have 4 electron groups, we can pin down our electronic geometry. It will always be tetrahedral. All right, tetrahedral. Once we know our electronic geometry, we can start drawing our 3-dimensional representation because every tetrahedron is the same. Oh, Diana, great question. Diana, it does for tetrahedrons and trigonal planar geometries. Things get a little weird in trigonal, Bipyramidal. And octahedra, which we'll get there eventually. All right, so drawing this 3-dimensional representation. 2 electron groups in the plane of the screen, 1 wedged coming out at you, 1 dashed going back behind you. Now, you can put your hydrogens and lone pairs anywhere in this depiction. I am going to put my 2 H's here and my 2 lone pairs here. All right, so we're on our way to our 3-dimensional representation, right? But now we have to account for 2 lone pairs. How does that change the molecular geometry? Well, if we look at it the way that I've drawn it here, if we just put those 2 lone pairs on our central atom, and you look at this geometry, you're going to say, Raj, just like you just pointed out, said that this looks bent. And it is. This is a bent geometry. But check this out. Take a look at its bond angle. If you're going, well, wait a minute, we already learned a bent geometry. There's bent trigonal planar, now bent tetrahedral. How do you tell the 2 apart? Well, we have 2 lone pairs on our central atom, so it's going to pinch this bond down even harder, 2 more degrees. Water has a bond angle of 105 degrees. All right, and that is how you tell the difference between a bent tetrahedron and a bent trigonal pyramid. A bent trigonal pyramid has a wider bond angle, a bond angle of 118, whereas a bent tetrahedron has a bond angle of 105 degrees. Cool? All right. So that is with those you can do the bulk actually of or maybe not the bulk. You can do a good chunk of the examples on exercise 5. But now we're about to get into a little more exotic territory. Let's draw the Lewis structure for pH5. Alrighty, so pH 5. This guy has a Lewis structure of, well, it's phosphorus with 5 H's attached. Phosphorus here is hypervalent, right? It has an expanded octet. It's breaking the octet rule. But that's okay because it's on the third period. It's allowed to. Okay, question from Raj. In the exam, do we say bent or the specific name? It honestly depends on the question. If the question asks for molecular geometry, the answer is bent. If the question asks for electronic and molecular geometry, the answer is tetrahedral. And bent. So it really just depends upon what the problem's asking for. All right, so we've got phosphorus. Now let's look at the number of electron groups here around our central atom. And we will see that we have 5 atoms. All right, 5 atoms. So 5 electron groups. Now, whenever you have 5 electron groups, you have a super cool geometry that is called Trigonal Bipyramidal. Trigonal bipyramidal. And here we have 0 lone pairs, so we know our molecular geometry will be the same. Trigonal bipyramidal. Now, how do you draw a trigonal bipyramid? Trigonal bipyramid is very interesting. The 3-dimensional representation looks like this. You have 3 bonds or electron groups in the plane of the screen, and then 1 wedged coming out at you, 1 dashed going back behind you. Now here we have H's on every position, so we put hydrogens everywhere. Now for the bond angle, this is super cool. Trigonal bipyramidal geometries have 2 bond angles. All right, they've got 2 bond angles. Now this is something that is unique up to this moment in time. Every position on every geometry has been the same, but here they're not. All right, I'm going to highlight the different positions using different colors. Now, these 2 H's that I've just boxed in red, all right, these are called the axial positions. And the reason why they're called axial positions is because they kind of sit on the axis. Like if this molecule was a planet, your axis is, you've got your North Pole and South Pole, and those are where those 2 kind of salmon hydrogens lie. Now the ones that are green, these are called equatorial positions. All right, equatorial positions, and they're called this because they kind of sit around the equator of the molecule. So that's the way to visualize this. You kind of have those 2 salmon H's on the top and the bottom, and then the 3 other kind of wrap around the center or the equator. All right, now the 2 bond angles you can have in this molecule is you can have a bond angle between 2 equatorial positions. So you have the equatorial bond angle, and you have the second type of bond angle is the axial equatorial bond angle. And as I said before, these two are different. All right, the equatorial bond angle is 120 degrees. All right, and then the axial equatorial bond angle is a perfect right angle. All right, so equatorial 120, axial equatorial, we have a firm right angle. All right, and you'll have to label both of these bond angles when you're dealing with a trigonal bipyramidal geometry. The reason why they're called the trigonal bipyramid is the geometric shape it makes is if you took two pyramids with triangular bases and put the bases together, it would kind of make a shape. It'd make a trigonal bipyramidal geometric solid. Raj, great question. So there is no bond angle of 180 for right now. There's no 180 degree bond angle because the equatorial H's are in the way. But as you'll see when we start adding lone pairs, those will surface up. All right, let's see. Okay. I am looking at the clock, and it is, we've been going, well, let's see, what time is it? It's 12:45. We don't have enough time to dive into the next thing, so I'm going to put a pin in lecture here. We'll resume on Wednesday, finish off VSEPR geometries, and then dive into hybridization. Definitely enough for you to finish exercise 5. Yeah. I want to pause here because our next kind of next example will be a little explanation intensive. So we're going to save that for Wednesday because I know some of you have to get to your next class. As always, I'm down to hang out. If you guys have any specific questions or things you want to get into, I am totally down. And if not, then I hope you all have an awesome Monday, and I'll catch you back on Wednesday. If there's no post class business that you guys want to get at. That is correct. As long as it makes it in today. Of course. Sorry, I can hear my toddler being a maniac on the other side of the wall. It's making me laugh. Alrighty, well, in the absence of any questions, I'm just going to go ahead and close down our stream here. Thanks everybody for tuning in live, and thank you to everyone who's going to catch this later. Hope you all have a rad Monday, and I'll catch you all on. Oh wait, question. Correct, Raj. That is correct. Still need to learn the of and yeah, you still need to learn the rest of the trigonal bipyramidal geometries, octahedron geometries, and hybridization. So you'll be 100% good to go as of Wednesday. Right now, you can hit most of them. I mean, you can draw all the Lewis structures, and then everything with 4 electron groups and lower, you can do the geometries for. But we still have a few more geometries to hit, which we'll be covering on Wednesday. You halted my sign off, and now I'm cautiously waiting in case more questions bubble up. And I'm sipping my Earl Grey tea. My toddler just said "Dada" through the wall. He it's been warm recently, right? So we got a whoa. We have one of those like little oh goodness. Oh wow. Wait, no, why? This is my computer's in battery saver mode. Which is weird. Oh man. Near dodge. Holy moly. I thought my computer was plugged in this whole time. It just said, hey, heads up, I'm in battery saver mode. And I was like, what? 20% of my battery left. Well, actually, it's 20% and 19%. The Surface Book, which I use for live casting, has 2 batteries. One in the main CPU and then one in the keyboard. So there's 20% in one and 19 in another. Glad to know it can last a whole live cast, though, I guess. Cool. Well, dudes, I will catch you Wednesday. Have a righteous Monday. Chill Tuesday. Come back for some chemistry and another killer mixtape. Later.